Okay, good afternoon all. Shall we start the class? I think this is what coming from last day. The non-standard decoders we discussed at the end. So you may remember the non-standard decoder that you may have this type of truth table. And based on this truth table, the usual way you can write output equations. And if it is possible, you can try to minimize those things. Then after that, we can draw the circuit. The same procedure you have to follow from the beginning also that we followed this one, the standard designing procedure. And the same thing you can apply for this non-standard decoders also. Okay. So today we can discuss the special type of non-standard decoder because we will use this one for the next circuit we are going to discuss. Because of that, it's also important. But anyway, that this type of things which may be non-standard decoders I have mentioned is one of the type, and many other types are available. For example, especially this is decimal to binary. Sorry, the other way. Binary to decimal, and then BCD to decimal, and then binary to gray. Likewise, the many type of non-standard decoders available. Okay, but today we are going to discuss about a different type. Then it's BCD to seven segment decoder. Okay, then I think you can hear me. Actually, you have seen this type of displays. I think in different cases that maybe you have seen. This type of displays. Okay, then there's a special naming convention for this one. Starting from this one, this is simple A, B, C, D, E, F, G. Okay. Then how many? We have several bars here. With this bars, we can make some of the numbers visible. Okay. For example, if you turn on BC, it will be number 1. Okay. Then depending on that, the particular number you can turn, the particular segment you can turn on. Then the particular number will be visible. But again, that why we have named this one as 7 segment, because we have used 7 segments to make this number. Okay. We have standard naming convention for this one, starting from very simple A, B, C, D like that up to G. We have used to name these segments. Okay, these segments may be LED or whatever the thing, light or whatever the light we can use, and sometimes it's LED and LCD, both versions are available. Both LED and LCD versions are available, but normally that LCDs, to drive LCDs, we need a special kind of driver. But generally, LED displays are available. That is, they are very easy to use. Okay. In our case, that today we are not going to discuss about that how to make those things like that. But anyway, that how to use these things in our digital circuits. That's what we are going to discuss today. Okay. Now you can see that, if you want to display number 0, okay, if you want to display number 0, what are the segments we can turn on? Now we have this type of display, then A, B, C, D, E, F, G. Okay, then to show 0 on the display, what are the segments we have to turn on? We have to turn on A, B, C, D, E, F. Up to F we have to turn on. Then G would be 0. Then we can give logic 1 to these segments, and G should be 0. If you do like this, then we can turn on the relevant segments and the number 0 will be displayed. Okay. Then if you want to display number 1, then we can give number 1 to BC and all other segments A, D, E, F, G, all these segments we can give 0. Then number 1 will be displayed on the display. Okay. Anyway, that now that we know that what to do that. Then in binary, we have several bit patterns here. Then we can send these bit patterns. In our case, that whatever the circuit we made, but if it is a number, then all numbers will be in binary format. But this 7-segment display cannot understand this binary format. Then we have to convert this binary format into a kind of code that this 7-segment display can understand. Okay. For example, what is the minimum number here we can display? Minimum value we can display here. What is that? It is 0. Maximum value is 9. That is the 0 to 9. The single digit numbers we can display here. Okay. If you consider this number 0 in binary, it is 0. For number 9, it should be 1001. Then we need 4 bits to give this number 9. Okay. In binary, 1001 is number 9. Then we take 4-bit code to show all these things also. Then we can make a table. On this table, we have this D, C, B, A. This is the number we are giving for the input side. And these are the segments we are going to turn on with the relevant pattern. Okay. Example, now DCBA 00 means what is the decimal value of this one? It's 0. Now next value is 00001. 00010. That is 2. 0011 is 3. 01004. 01015. 111. This is 6. Seven, 8, 9. Okay, up to this that we can fill that we fill this table, try to fill this table, and here this is the 7 segment display. A, B, C, D, E, F, G. Okay, now from binary side, we have this 000 value, that is binary 0. But when we have this value 0, we want to show number 0 on the 7 segment display. Okay, and to do that, you can see here in this table we have some kind of conversion. Okay, we have some kind of conversion. Then this binary number should be converted into this 7 segment readable code. Then to do that, we need some kind of circuit. Assume that this side from this side we can think this circuit is generating binary numbers. Binary numbers. It may be 4-bit. Okay, then here this is D, C, B, A. Okay, then here we have 7 segment display. Okay, here we have 7 segment display. Like that. And for the inputs, we have 1, 2, 3, 4, 5, 6, 7. They are simple A, B, C, D, E, F, G. Those are the relevant input values. Now we need a kind of circuit in between these two modules. In these two modules, in between these two, we need a kind of circuit to take this binary code as input and to generate this 7 segment display understandable code as output. Now we want to design this one. This circuit will convert this binary value, binary to 7-segment display compatible readable code. That's what we are going to do. Then for this type of non-standard decoder, now we know the number of inputs. We know the number of output lines also. Now we are making this truth table. This is this 7-segment decoder truth table. Okay. What this decoder does is that when it receives the 0000, it will generate these output lines. That is, this A is 1, B, C, D, E, F. This value it will generate. Then these values are going to the 7-segment display here, and it will turn on the relevant segments. Then number 0 will be displayed. Okay, here to show number 1, then BC will be 0 and all others like that. What about number 2? For number 2, C and F, they are 0, 0, and others are 1, 1, 1. Then number 3. Number 3 is EF should be 0, 0. EF. These 2 0, 0. These are 1, 1, 1. Shall we complete this truth table? Isha, is it okay now? Now can you understand? Okay. Yeah, fine. That can we try to complete this truth table up to number 9? Okay, for number 4, A0, DE00. Number 5, DE00. DE0. Number 6, DE0. 7, DEFG. 8 all, 9 EC. After 9, what can we do? After 9, what are the available values? Then it's 10, 11, 12, 13, 14, 15. Those are the available values. But for these values that we cannot display those things in a readable format. Okay. For number 10, we need 2 digits. But in decimal system that if we use single digit in decimal, we can show only 0 to 9. But if you want to show number 10, it's a 2-digit number. Then we need another display. Then using one display, whatever the thing that we can show is 0 to 9. Then we are not going to use this part, these numbers, to show these values on the display. Okay. Then what can we do? One thing you can do is, for any of these patterns, from 10 to 15, you can turn off the display. You can turn off the display means you can put zeros for all these 10 to 15 codes, 10 to 15 these 6 values. You can put the 6 values. You can put zeros like this. Okay. Then we can put 0, 0, 0. This is one way of doing this. Or maybe you can put X, don't care. We don't care, because that if you know that your system, in your system, this binary number generating system, whatever the system is, not going to generate numbers beyond 10, then you don't care. Okay, but it's up to you. Whatever the way that you can put this 0, or maybe this X, or whatever the thing, like that. Okay. Then after that, we can finalize for all these things. That's a Okay, then actually we don't care about this one, and different manufacturers have taken different steps, and some of the manufacturers they have used hexadecimal code to show these values. But in our case, we don't care about hexadecimal. We are considering only decimal values. Okay. Sorry that I was muted. Then here we can now you know how to design this one. Generally, what we can do is that you can write output equation for simple A, simple B, simple C, like that up to simple G. We can write 7 output Boolean equations. Then if it is possible, we can minimize this one and we can design this binary to 7 segment display. But in this case, we have a problem here. But when we say binary to 7 segment display, we haven't taken all 16 patterns here. From the 0000 to 111, 16 patterns are there. All binary 16 patterns are there, but we haven't taken all 16. We haven't taken the last six patterns. Because of that, we can't say it's binary to 7 segment decode. Okay. Instead of that one, we have to say it's not binary. Okay, then we can say it's binary coded decimal. Why? Actually, we are going to convert this one. This is binary value, but the final output is a decimal output. Then we have the binary value coded into decimal. Then when you consider the decimal, we can display only 0 to 9. When you say BCD, binary coded decimal, then we are handling with only 0 to 9 numbers. Then no problem. Then we can say this is BCD to 7 segment decode. Then we develop this BCD to 7 segment decoder to do these things. That can you recall your the first steps that we have to follow? First step, we should identify number of inputs and number of outputs. Now we have done that one. From capital A to capital D, we have 4 input lines. That is for binary number input side. The other side, to connect the 7 segment display, we need simple A to simple G, 7 output lines. Now, after identifying this number of inputs and number of outputs, we have to prepare truth table. And then we have to include our conditions or whatever the things they are. Now we have prepared the truth table. Next step is writing equations for the simple A, simple B, like that, up to simple G. We can write 7 output equations, then minimize those equations. Okay. we have minimized these equations, but in this case, it's a large number of equations and large number of terms are there, and we are not going to do okay. Then you know those tips. But anyway, that we are not going to do this one because that it may, if you are going to do this one, it may be hundreds of kits we need to design this one. But we don't do that one. Anyway, we can buy those things without designing those things readily available in the market. Then we can buy this one as a very small chip. But if you are going to design this one, it might take nearly A4 sheet size circuit may be there. When you use standalone gate ICs and use for these things for the development, it may be that type of circuit. But in this case, we are not going to design that one, but you should know how to design. Then BC to 7 segment decoder, and whatever the circuit, and if you are having here, you can have this binary, whatever the binary number generation, the binary bit pattern generator circuits here. And if you want to connect to show your number on a display, okay, then we can use BC to 7 segment decoder in between these two. Then finally, you can show your number on the 7 segment display. Now, is it okay? Now, do you have any idea that the designing steps are okay, very simple, but don't think about that. Right, if you want that, I can write equations for this one here also. This is A bar, B bar, C bar, D bar we have. And what is next? Then A bar, B, C bar, D bar like this. Then you can write these equations. I'm not going to write these things, but lengthy equations may be there. Oh, simple A, how many ones are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 ones are there. Then you can have a fixed 4 variable Karnaugh map, and you can minimize these things. Okay. But we are not going to do this designing part, but anyway, you should be able to understand that one, and you should be able to explain it. Okay, then finally our target is to use these things for any kind of circuit. Up to this point, is it okay? Then actually we started our discussion to discuss about non-standard decoders, but this is a one very popular non-standard decoder. This is not 4 to 16 kind of decoder. We have 4 input and 7 output lines. But generally you have 4 input decoder. It's a 4 input lines are there, then 16 output lines may be there. It's a non-standard decoder. But this non-standard decoder, they can have the different number of inputs and different number of outputs. But anyway, it's a decoder, non-standard decoder. And we should know their truth tables and how to make those things, how to design those things. We have to have that idea. Okay. If you are interested, that I'll show you real manufacturer data sheet about 7 BC to 7 segment decoder IC. Yeah, this is the manufacturer is Fairchild, and they have developed this one is in 1986. And this is a BC to 7 segment decoder IC. And these are the number of pins. You can see this is a 16-pin chip, 16-pin IC. Okay, it's a very small one. And this is the truth table of it. And you can see that the DCBA inputs are there, simple A, B, C, D, E, F, G, output lines are there. Okay. Some other different special inputs may be there, but please don't care about those things. We are not interested about this one. Only the thing that this DCBA, this part, and simple A, simple G, that part. Those output columns we can consider. And this is the circuit after minimizing all these things. This is the circuit we will have. That's why I say that 100 of gates may be there. But we are not going to design those this one. And many other information also there. It may be some useful information for the circuit designers, but we are not going to design this type of circuits. And we are not going to use this in the labs also, but our primary concern is for the designing part. For the implementation part, when you want to implement this one, then you, without designing this type of things practically in the lab, you can buy this type of ICs. It may be around less than 100 rupees, maybe a couple of years back before this pandemic comes. But these days it may be around 200. Okay. And you can see this is the real package one, and this type of ICs you can see that there. Okay. You can see the number on that is 7447 is the IC number. When you request 7447 IC, so all over the world it's standard. It will be BC to 7 segment decoder IC. Okay, then okay, anything, any question? Any question regarding these sections? Why do we write the inputs in the order of DCBA? Can't it be ABCD? Okay, question is there that asking that why do we write these inputs in the order of DCBA? Normally that I have written it purposely. It's not a mistake. that actually after completing the next lesson, you will realize that why we have written these input lines in this order, DCBA, reverse order, without writing it as ABCD. Anything else? Any other question? Okay. If you are okay with that, then we can finish this non-standard decoder section now, and we can move on to the next part. But until that, if you have any kind of question, maybe not about this one, any kind of decoders we have discussed previously, can you consider this one also? Any question? Okay, if you don't have any question, then we can move on to the next section. Actually, this one is, I think you may remember that we discussed this standard decoders and non-standard decoders, all these things under combinational circuit. Okay. This section is actually that now we're going to, this is sequential circuit. But so far we have discussed combinational circuit. Now, this is the next section. We're going to discuss. This type of circuit so far we haven't discussed. The previous one, all those circuits so far we have discussed, they are falling into combinational circuits category. The entire digital electronics we can divide into two sections. One is combinational circuit, the other section is sequential circuits. Okay. When it comes to the sequential circuit, it's not like previous circuits. These circuits are having some kind of feedback action. Okay. They have feedbacks. Previous circuits that we haven't mixed inputs and outputs to make circuits. But in this case, we are combining outputs to inputs to make this type of circuits. Okay. Then with the sequential circuits, and we are introducing a new type of basic building block, that is flip-flops. Okay. This flip-flops is having actually this input-output feedback action there. Anyway, that we will discuss this one later on, but then basic building blocks. This is flip-flop. Okay. Then actually many types of flip-flops are available, but we are not going to discuss about all these flip-flop types, but we are discussing only about necessary type of flip-flops. Okay. Very basic type of flip-flop is first one is RS latch, and second one we are going to discuss is JK flip-flop. Third one, D-type flip-flop. Okay. Those are the three major flip-flops we are going to discuss, but in between these three, we have some other types also. We'll discuss those type then and there. But this is pretty important to understand about these flip-flops. So otherwise that we can't understand the sequential circuit, because it's the basic building blocks of the sequential circuit. Then this flip-flop we can consider, which is the basic building block of sequential circuits. The other point is this one, so far we haven't received this functionality from any kind of circuits we have discussed. This is, we can consider this as 1-bit memory. Any kind of memory circuit so far we haven't designed, and we have found them. Okay. I feel that if you consider any kind of digital circuits without having memories, it's not possible to make digital circuits. All the circuits, most of the circuits, they are having memories. Then if you don't have memories, then basically we can't do very good designs. Then this is very important to discuss about flip-flops, because flip-flop is the major component involving to make memories. Okay. Actually take this RS flip-flop without wasting our time. This is RS latch. It has two outputs. This is this one is complementary output. Okay. Here we have one input. This is R. This is the other input. This is S. Okay. Here this R is 1. We say this reset input, and this one is set input. That is how this R and S, these values are coming, these letters are coming. And the other side you can see it's not two different outputs, but physically we have two lines there, but logically it's same out Q and Q bar. Q bar is the opposite status of the Q. Because of that, it's not a two different outputs. Then truth table of this is zero zero. We can give 0 1 1 0. These are the all possible combination for R and S. Here you have to understand one thing there. There should be a timeline here. It's not like previous circuits we have discussed so far. This is the timeline. Why do we need timeline here? Very carefully understand this one. But when you want to design, when you want to find this value of Q, how can we find value of this Q? It's basically based on two input. This is a NOR gate. Then this R is the first NOR gate output. Then to determine Q value, then you have to take two input values, and then you can easily determine output value. Then what is Q here? Can you write Q in terms of R and S? What is Q? Q is basically we need R. That is one input. The other input is Q bar. Then it's sorry. This is R plus Q bar. It's NOR gate. Okay. Then when you want to find Q bar is there. What is Q bar? Q bar is an output. Okay, then we will find Q bar. What is Q bar? When you want to find Q bar, then we have to find the two input lines there. This is S. One input is S. The other input is Q. Okay. When we want to find, the other one will come. Then there's that's why I told you at the beginning, it's a kind of mixture, kind of feedback. Loop is there with input to output, output to input, like that. Okay. Then when you determine this Q output value, Q bar is there. What is Q bar? Q bar is another output value. Okay. Then when you decide the present input values, we have taken previous output value in order to make this present output value. Did you understand that one? When you decide the present input value, we have to take the previous output also. It's a mixture of previous output and present input values. Then we combine this previous output value and present input values to make this out. Then this timeline, we have to carefully understand that these things are there. And we have three things here. Now this is present. This is present Q. Then we have previous output value. That is previous Q. And next Q also may be there. next output also may be there. Okay. Then we have to understand this. When you determine this present Q value, we need to take previous Q also, because based on the previous Q value and the present input values, then combining these two, we will make this present Q. It should be present. It's present. Okay. Then here we are using a small notation here. We put this Q plus for present Q, and previous one is Q, and next one is Q plus plus. Likewise, to show that the two different places of the timeline and about the two different values of the output depending on the time. Okay. Then here we are finding Q plus value based on the present input values. Then the truth table output is this one. What is this? This is R0. What do you mean that? What do you mean by this one? Here you can see this R is having a special meaning, that is reset. S is having another meaning, that is set. In this combination, what do we ask? We ask flip-flop to set the output. Setting output means what does it mean? What does it mean that they are setting output? When we set some kind of value of a circuit, what do you think? It will be, the output value will be 1. Then this output should be 1. And here in this combination, what do we ask? We ask reset the output. When we reset the output means we are receiving 0. Okay, here what do we ask? We ask nothing. We don't ask to reset and we don't ask to set. Then circuit will have the previous value. Why? Previous value is there, it's remaining. Why? We are not going to change this one. Okay. What about this one? Last combination. Last combination is at the same time we are asking to reset and set. It's not possible. Because of that, this should be forbidden. And this using of this combination is illegal. Okay. And it should be avoided. Then anyway, that we have 2 inputs and we are having 4 combinations. But although we are having 4 combinations, one is not possible to use. That is one of the problems of this RS latch. Okay, up to this point, do you have any question? Is it okay? Okay, I'll explain this one again. But anyway, that I have a power cut. Anyway, the laptop we have power until hopefully that we can finish this lecture without any disturbance. Anyway, can you explain again how you got the outputs? These outputs, the truth table actually, this design is that this design purposely they have decided from this Q and Q bar outputs we need two opposite things. Same output, opposite value should be there. And this RNS inputs, the designers have decided when you give the values to this R, when R is 1, output should be reset. When SC is 1, output should be set. That's how this design is coming. Okay. According to that one, and when you consider this combination, what is the meaning of this combination? Here S is 1. S1 means we want to have the logic 1 at the output. That's why when you give this one, output will be 1. Okay. Then when you consider this combination, this one, here R is 1. R1 means we want to reset the output. Then we have 0. Okay. But in this case, what do we say? We don't say to reset and we don't say to set. That means we are doing nothing. Doing nothing means then we will have the previous value remaining. Then what is previous one means it's Q. In the timeline we have this one. We have this notation. For the present value we say it's Q plus, the previous value is Q. But this 1-1 combination is not a valid combination. It's an invalid combination. Okay. This is invalid. Because of that, this one should be avoided. Is it okay? Okay. Then actually that we have identified already that with this RS latch, one problem is there. What is that? We cannot use this last combination. This last combination, this one, we cannot use. This is our first problem. This is first issue of this RS flip-flop. Actually, the second issue is also there with this RS flip-flop. Sorry, RS latch. That is, imagine that, okay, hereafter we don't draw this detailed diagram. Instead of that one, we draw this one. Then this is one output. This is Q. This is Q bar, R, and S. Okay. Assume that in this case you have this R and S value. Then depending on this value, then you will have this output value also. In one time, you have given 0, 1 to these inputs. Then what will be the output? Output is 1. Why? We asked to set. Okay, then in next time, we want to change this. We want to change this input values to. We want to change this input values to this one. Okay. Now, at the moment we have given R0 S1, based on that output is 1. Next time we want to change this R0 to S1 to 1 0, expecting output is 0. Okay. How do we do this one? How can we give 1 to the circuit? How can we give 0 to circuit? Actually, this 1 means this logic 1 means we are giving plus 5 volts to circuit. 0 means we are giving 0 volts to a circuit. These circuits cannot understand ones and zeros, so whatever the letters, circuits cannot understand. Circuit can understand only the thing is voltages. We have to give these voltages to circuit representing logic 0 and 1. To represent logic 0, we give 0 volts. To represent logic 1, we give 5 volts. And how can we do that one? Then we have to interchange these values. Now this case R is 0, S is 1. Now we want to interchange these values to R1, S0. Then using 2 wires, we have given these input voltages. Okay. Then how can we do that one? Assume that okay, now we want to change this. We want to change this 0 to 1. Okay. Assume that we have changed this 0 to 1 here. Now we have changed this one. But still we are doing it manually. Still we couldn't change this one. Still 1 is remaining. In next stage, we are changing this 1 to 0. Still this 1 is there. But when we are changing these two values to the other values, then this 0 we have changed little bit quicker than the other one. Then because of that, still we haven't changed S. We have included this 1-1 combination there accidentally. Why we are doing it manually? Then because of this result of this one is unpredictable. It should be avoided. We don't know what value will be there. Then because of that, this unnecessary intermediate stage may be there. This unnecessary intermediate change, stage may be there. We don't want. Then if you are watching these output lines, if you have connected this output to another circuit, something like that, this is another circuit, and this circuit will do some kind of maybe the important work there, depending on the Q value. This circuit will take some kind of decisions depending on the Q value, but this Q value, we don't know what type of Q value will be there. And this is unnecessary one. Then because of to avoid these intermediate stages, what we have to do actually, as a result of what we have these intermediate stages. If it is possible to change this R and S values simultaneously, if it is possible to change these R and S values at the same time, these intermediate stages will not be created. These intermediate stages will not be there if you change these values at the same time. But the problem is that we can't change these values simultaneously. Okay. Then this is the second issue of this RS flip-flop. What is the second issue? The first issue we have already identified. The second issue is input values cannot be given simultaneously. Okay. At the same time, we cannot give this. Then this, now how we can find a solution for this one? How can we rectify this one? What is the solution for this one? Okay, now you can find a solution for this one. Why? Now you know how to do this one, because this is the RS flip-flop. This is our RS flip-flop. This is Q, Q bar. These are the two output lines, and this is R and S. Now we have to have a kind of circuit here, and this circuit will receive R and S values from the outside, and after that we can have a control input there. Okay, this control input can have 0 and 1. When 0 value is there, we are not sending this R and S values to the original R and S flip-flop values, flip-flop lines. We have time. The user can have any time there. He is having freedom to change these R and S values, taking his own time. And after setting these values, we put this control input to 1. Then all of a sudden that we put this value to 1, and both the circuit is receiving that one, then both these R and S values will be transferred to the flip-flop R and S values, R and S inputs immediately at the same time. Now you can design this circuit. Why? It's a combinational circuit, and you know how to design a combinational circuit. It's not sequential. If it is sequential one, then you need this type of feedback loop or something like that, and this flip-flop should be there. But we are not going to do that one. We have flip-flop separately, but we need this additional circuit here for what? Make those inputs simultaneously go into the flip-flop. Shall we spend a couple of minutes and try to do that one? Okay, here to do this one, we can consider this electronic switch here. Can you consider this one? This is a concept of electronic switch. Then you have this input A, and you can take this as control input. Okay. And this is your output. When A can take 0 value here, and 0 or whatever the value, then if this control input is 0, if this control input is 0, A is 0, output is 0. Then this A is 1, but it doesn't matter, control input is still 0, then output will be 0. Whether A is 0 or 1, output will be 0, 0 when the control input is 0. Now, assume that control input is 1. When control input is 1, when A is 0, what is the output value? It's 0. And still control input is 1. Now, value A is 1. Then output is 1. Now, you can see that. You can see that here, this one, this one. When control input is 1, whatever the value we have given to A is coming to the output. Then we consider this is kind of electronic switch. When this is switch on and this is switch off. Okay, we can use this one. We can use this concept to find solution there. The solution is something like this. Now we have this flip-flop here. We have this flip-flop and this one. R and S inputs are there. Now we are introducing this part of the circuit. We introduce 2 electronic switches here and combine these 2 control inputs together. Then we can have 1 control input here, and these are the R and S values. Okay, then whatever the way that you can, when you give 0 here, giving 0 here, the user can take that whatever the time he wants to change this one, and he can put this 1 or 0 value, whatever the value is there. Then we will change this 0 to 1. When you change this 0 to 1, then here is 1, here 1, here 1, and this one will come here, and this 1 1 will, then output is 1. This 0 will come here, this 1 0, output is 0. That's what we need. We want to give 1 to R, then R has received 1. We want to give 0 to S, then S received 0. That how R and S, they have received these values. Whatever the time that you are changing this 0 to 1 at once, these R and S outside values will be transferred to the input inside R and S values. Okay, then this new one, then when you consider the thing you have done here, it's 0, we have changed to 1. After that, we will bring back to 0. It's originally 0, and to give these input values, we have taken to 1, and after that we can bring back it. This a kind of clock pulse. Because of that, we name this input as clock in. Okay. Now with that, we can address the second issue. Then what about the truth table here? Now what will happen to the RS latch truth table? Zero, 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 one, 1, 0, 1, 1. Have we touched the inside things of the flip-flop? No, we haven't touched anything inside the flip-flop. We have added something outside. Because of that, the flip-flop truth table will not be changed. But one thing will be changed. What is that? This timeline. Here, this timeline, instead of this present queue, previous queue, next queue like that, we have clearly two different things. This is queue. This queue is after applying clock pulse. Because after applying clock pulse, then only this output will be changed. Because when you apply clock pulse, then RNS value will be transferred to the inside. Then flip-flop can determine the output value. Until you apply this clock pulse, output will not be changed. Then after applying the clock pulse and before applying the clock pulse is clearly two different things. Before applying clock pulse. Then we have a naming convention here. For this one, we put Qn plus 1. This is Qn. Then this truth table, we are finding this one Qn plus 1. Then here output is 1. Here output is 0. And this is Qn. Qn means previous. Still, this is avoided. This is invalid. And this special type of arrangement, we'll give a different name for this one. This is clocked RS flip-flop. Whatever the flip-flop is having a clock in, whatever that latch is having a clock input, we call it a flip-flop. Okay, that's the difference between RS latch and clocked RS flip-flop. Then the block diagram of this one is something like this now. It's Q and Q bar. They are as it is. And we have R input here. We have S input here. In addition to that, we have this clock input. Okay. Then this is how clocked RS flip-flop block diagram. And what is the difference between here? We have added one control input called clock. And the function of this one is after applying a clock pulse, then only these input values will be transferred to the inside the flip-flop. And after that, it will determine the output value. Okay, why do we have this RS clock input flip-flop? To find the solution for second issue of RS latch, then we can simultaneously give input to this one. Okay, the second to have a issue for the first solution. Actually, we are not going to discuss this in detail. Instead of that one, I'll say the solution straight away. I'll mention there. The solution is JK flip-flop. JK flip-flop. Okay. I'll draw the JK flip-flop and put the truth table there straight away. And it is not necessary to find the internal details of this one. We can take it out of scope like that. We have this Q and Q bar there. And we are not going to discuss that how this J and K came. And here also we have clock input. The truth table of this J and K flip-flop is something like that. It's having clock input, then Qn plus 1 is there. 0, 0, 0, 1, 1, 0, 1, 1. Okay. Then for this one, it's Qn. This is 0, 1. For the solution of this one, we have Qn bar. Okay. If you are really interesting to find that what is inside JK flip-flop, you can refer any kind of standard book of digital electronics. Then you will realize that how they have changed RS latch, RS flip-flop to come to this stage. But in your scope, I am not going to discuss those things, and this will not come to examination also. Straight away, we have jumped to the J and K flip-flop, and third one also we can come. Actually, here for these stages, we have special names for this one. This is, we can say, this is previous. This previous, and we have a special name for this one is toggle. When you have 1 1 for J and K, it's always it's coming Qn and Qn bar. Previous state inverted bell. Previous state inverted bell. Like this. Okay. The third flip-flop type is D-type flip-flop. It's a modification of this JK flip-flop. JK flip-flop is something like this. Q bar. This is JK and clock. We have placed NOT gate in between this J and K, and this is the clock input. This is clock, and we say this is D terminal, and this is D type flip. Okay. Can you find the values of D flip-flop outputs? Then when you give 0 and 1 here, when you give 0 and 1 here, can you spend a couple of minutes to find these output values? Okay, then what is the output value here? Then when D is, we can determine here, when D is 0, J is 0 and K1. When J0, K1, J0, K1, what is the output value? It's 0. Okay, then when D is 1, that means J1, K0. Then J1, K0, what is the output? It's 1. Okay. Then when you give 0 to D type flip-flop, output will be 0. When you give 1, output will be 1. Then why this is important? It's not like previous ones. Actually, this is the type of flip-flop we can use for data storing. When you give whatever the value, it will remember this one as it is. Because of that, among all the flip-flop types we have discussed, this one is the useful one for data storing. Others are having the specific functions, but this is the only one we can use for data storing. This will remember whatever the thing it has received as it is. Actually, this D type flip-flop, D means this is data type flip-flop. Data type flip-flop. Okay. Actually, those are the flip-flop types of we are going to discuss. I think we can discuss other section next day. Any question, anything regarding section so far we have discussed? Okay, if you don't have anything else to discuss, then today we can finish the class. I think the power of my laptop is almost finished, that it's 6% remaining. Okay, we can. Okay, then shall we finish the class? And thank you very much for your participation and time. And we will meet next week. Until that, take care of yourselves. Thank you very much. Have a nice time.
Thank you, sir.
Thank you, sir.
Okay.